Alright, today's problem is the newest smaller values. So what's going on here? So we have some array, and for each position in the array, we want to find the nearest index to the left with a smaller value. So for example, the array is 2, 5, 1, 4, 8, 3, 2, 5. So 2, well, there's nothing to the left, so 0, not found. 5, the smallest thing to the left, to the left we have a 2, which is smaller, so the answer is 1. 1, there's nothing smaller than 1, so it's 0. 4, the 1 is smaller, so the 1 and the 2 are both smaller than 4, but 1 is closer, so we output 3, which is the position of the 1. 8, the 4 is the closest smaller thing. 3, the 1 is the closest smaller thing. 2, again, the 1 is the closest smaller thing, and 5, the 3 is the closest smaller thing. So that counts for our outputs. So how can we actually do this? So if we just checked sort of all of the possibilities for each position, that would be like an n-squared solution. But for the 5, you could check the 2 and the 3 and the 8. I mean, for the 5, it looks like pretty quickly, but for the 2, we could check, the 3, the 8, the 4, and the 1, and then we'd be done. But this is n-squared, because if you might need to go, you might need to check everything. Like if the array is given in descending order. So we need like n log n instead of n squared. And we can actually do that with a map. So let's see the idea. So 2, 5, 1, 4. So let's just graph these points. The x value is just the index. So 2, 5, 1, 4. So the idea is going to be, as the 4 comes in, so we're going to add things one by one to our data structure, which is going to be a map. Right. So the 2, fine, it goes in. The 5, then when the 1 goes in, there's something interesting to notice, which is that there's no point in having the 5 anymore, because 1 is a better answer. It's smaller than 5, so it works for more numbers, and also it's closer to everything to the right. So we can actually delete the 5 when we put in the 1, and we can delete the 2 for the same reason. Anything that the 2 would work for, 1 is a better answer. 4, we actually can't, we can't cross off the 1, because if we got a 2 later, we might need the 1. But if we got a 5, we would want the 4. So 1 and 4 are both still valid answers. The next thing is an 8. So 8 is again a valid answer, because if there's anything higher than 8, 8 is the best answer. But if there's a 2, then we have to use the 1. So a new number is valid as long as it's increasing, right? The valid possible answers are going to form some increasing thing, increasing both in index and also in value. So after the 8 comes the 3. And then when you get the 3, we can cross off the 8 and the 4, because 3 is just a strictly better answer than 8 or 4. Right, and this is actually the same as maintaining this sorted condition, right? So another way of thinking about it is that 3 was less than 8 and 4, so that's why we get to cross them off. Then we get a 2, which is better than the 3, so the 3 is no longer a valid answer. And then we get a 5, which is also valid. And so as all of these numbers are coming in, I explained how to sort of add them to this data structure, but I didn't explain how to actually use the data structure. So if you get a new value, right, and you want to look at the value, the answer, let's say it's here, you just find this biggest thing that's smaller than it, so this guy in that case, and then you output that. And the reason for that is because they're sorted, things in this data structure, by value and by index. So you need something that's smaller than it, because that's the rules, right, the smaller value. And you want the biggest thing, because the biggest thing is also going to have the biggest index, right? And you want the newest position to the left. So that's the solution, is we're going to maintain this map. And whenever, for every new value, we're going to query into it, find the biggest thing that's smaller than that new value, And then when we add the new value, let's put it in the map, and we'll delete any previous values that are bigger than it. So let's do that. Use smaller values. So we got n and then just an array. Fine. I think technically we don't even need to store this in the array. We can just sort of do it online. Whatever. So we're going to have this map. So we want something smaller than it. So we're going to use the upper bound function on that. So that returns something that's greater. So the way that we can solve this is just by reversing the order of the map. So normally maps are sorted from low to high, and upper bound gives us a bigger thing. But we're going to sort from high to low, and then upper bound is going to give us a smaller thing. So if we actually found something, then we got that thing. This is the index, and it's supposed to be space separated. And if we couldn't find anything, then it's 0. Okay, so that was the query part. And now we need to do the adding part, which includes crossing things up. So if the most recent thing in the map, which is the biggest thing, which is n.begin, so if it's actually has something in it, wait, it's not empty, and the biggest thing in it is bigger than our new value, then we get to delete it. And by the way, if it's equal to the new value, then we still get to delete it because the new value is going to have a better index. So if it's greater than or equal to, so we delete all of those values, and there might be several of them. But we know it's going to be like a suffix of the map, because the map is sorted by value. So once one thing can stay, everything after it is smaller, so it can stay as well. And then we add this value to the map. And the index is like one index positions, so I plus 1, and this new value, and a new line, and that should be it. Okay, so I'm going to go and choose, I assume vector, we need, whatever, map functional gives us greater, right? That's what we use to reverse the order of the map. And then we need space stored and 64-bit integers. Does not compile. What's going on? I said greater than equal to A, that doesn't make any sense. Greater than equal to AI, that's the value that we're going to add. 0103437. That looks good. Smaller values. Cool. So that worked. Yeah. So this is think of it as like an optimization of the n-squared solution. So we have this data structure, which just stores, I don't know, like all the increasing, right, all the positions that are increasing in both. Sorry, the best way to put it is all of the possible answers, right? And the point is, you can't be a possible answer if you're bigger than a new value, because the new value is just better, right? Everything that you are smaller than, this new value is also smaller than, and also it's closer, and you want to find out the closest thing. So all of the possible answers are sorted, from low to high. Right, that's what makes it a possible answer. Right, like 1 is possible even though we have a 2, because if we got another 2, we'd have to output the 1. So that's what this map is doing. So then upper bound in this reverse order map is giving us the first element that's strictly smaller. So if we actually found something, then we print it out. If we didn't find anything, then we print out 0 if we're not found. Then we delete all of the things that are no longer possible answers because the new value is better than them. And they're always going to appear sort of at the front or at the biggest things in the map, because once we find something that's smaller than AI, everything below it is also going to be smaller, right? Because the map is sorted by value. So anyway, we throw out all of those things that are no longer valid possible answers, and then we add our new thing, which is always a valid possible answer, because it has the best index. So anything bigger than it should have it as an answer. And that's it.